So all of you to the tutorial track 1.2. I guess you guys will be migrating from the main session to this particular room or track. So the topic for this tutorial 1.2 is validation of complex safety architecture. And as you have been listening from our vision talk to keynote and today's keynote as well, that automotive and automotive electronics is becoming bigger and bigger, and there are tons of verification challenges around this. And safety architecture is key part of the automotive domain chips as such. So today we have Vedang Garg, who would be taking us through this particular tutorial about complex safety architecture. Let me introduce all the authors. So Vedang Garg is Functional Safety Solution Architect for Siemens EDA. He is responsible for defining the core safety analysis and FMEDA solution. He holds a master degree in computer engineering from University of Massachusetts, Lowell. Prior to Siemens EDA, Vedant was part of the core IC verification R&D team at Cadence. And the other the co-author is Anne Keffer. Anne Keffer is the worldwide product marketing manager for functional safety verification at Mentor Graphics. Anne started her career as a software developer for Hewlett-Packard, writing operating system codes. After a few years in R&D, she moved to the application engineering, and then in the product marketing, and finally in marketing management. She has since led worldwide marketing and product management for companies in the automation, robotics, and automotive functional safety into verification industries. She joined Mentor, a Siemens business, in June 2019. And our last co-author for this particular tutorial is Samson Wong. Samson Wong is the staff design engineer at ARM. He has over 30 years of industry experience, spanning from engineering management, architectural definition to the silicon debug, and system bring up at Intel, Sun, Oracle, and ARM. So over to Vedant to start your tutorial. Thanks.
Hi, and welcome to our tutorial titled Validation of Complex Safety Architectures. I'm Anne Keffer, Product Manager of Siemens EDA Ostemper Functional Safety Tools. I'm joined by Vedant Garg, who is a Senior Product Engineer for the same tools. And we are joined by Samson Wong, who's a Staff Design Engineer at ARM, who's used our tools for safety analysis and is going to tell you about his experience. I'll start the presentation discussing some of the challenges of developing chips for the AV/EV market, and I'll describe the typical safety workflow. Then Vedant will talk about the details of safety analysis, and then he'll hand it over to Samson, who will describe how he used analysis for his design. Then Vedant will finish the presentation discussing how to optimize fault simulation, and will show a demo on closing the loop from analysis to validation. And then I'll continue the tutorial, or I'll conclude the tutorial rather, and Vedant and I will be available for questions at the very end. So functional safety involves all parts of the development process, including specification, design, implementation, integration, verification, and validation, as well as the production process. It also requires you to build an organization that designs chips around specific demands of the automotive safety standards. Training is required, additional processes must be added to development and production, and documentation must be collected and prepared to achieve an ISO 26262 certification. These unique steps add significant expense to the development of chips for the AV/EV market. You start development with a hazard analysis and risk assessment, or HARA, to identify the malfunctions that could possibly lead to electronic system hazards and assess the risk associated with them. A HARA leads then to developing safety goals, which actually becomes part of your failure mode effects and diagnostic analysis, or an FMEDA, which Vedant will talk about in more detail later in this presentation. And there are actually additional steps in between the HARA and the FMEDA that I'm not mentioning in this presentation. But to achieve certification, you need to prove you've complied with the ISO 26262 standard by providing documentation that covers the personal involvement in development and testing, the processes used to develop the solution, and the fault analysis of the product. So as you can see, developing chips for this market is challenging in many ways and takes more time and effort than making chips for non-safety critical markets. So what do you want from your functional safety tool chain is really the question. And what you want is accurate metrics so that you know that you're reaching the optimal safety architecture for your target safety level. You need scalability, you need automation to accelerate the process of getting certified, and you need assurance you can complete a compliant safety campaign. So getting a little deeper into what it takes to achieve an optimal safety architecture, again, you're starting with safety analysis, and this step indicates design susceptibility to random hardware faults. So the analysis is typically completed by safety engineers who are experts in the area, but an analysis tool can make this step more efficient by performing structural analysis of the design and accurately calculating the metrics needed to predict the level of safety of the existing architecture. If the design hasn't achieved the desired safety level, or more accurately, the ASIL target, the analysis tool can guide you to explore ways to identify how to achieve your target ASIL level. And then once you identify what you need to do to achieve your ASIL target, you can use the instructions that you get from the analysis tool to insert additional safety mechanisms into the design. There are also tools that automate the insertion of safety features, accelerating the process of insertion and providing design consistency. And then next, you perform fault injection to establish the effectiveness of your safety architecture and ultimately prove that you've met those ASIL targets. So these tasks contribute to delivering work products that are actually required to pass a safety audit. So this picture shows a typical safety workflow. It starts with planning, which includes determining safety goals, making sure your organization has expertise, and then the development of the FMEDA. And then you move on to the safety assessment analysis to understand the current state of safeness in the design, and then you make modifications if necessary to meet those safety targets or ASIL level. And then next, you run your fault campaign to inject the faults and get results. However, if the resulting metrics from the fault campaign don't reach your target ASIL metric, you must go back to analysis and start the process all over again. And iterations around fault injection can take months and months, actually, and are very, very costly to the development cycle. So customers that we talk with are looking for ways to reduce iterations around fault injection because it is costly and they really need to reduce their time to certification. So in this next section of this webinar, Vedant will talk about techniques used during the analysis phase of the safety workflow to reduce iterations around fault injection. Vedant?
Thank you, Anne. I will be starting the webinar discussion using talking about safety analysis. Basically, the safety analysis, before we get into the details of safety analysis, let's look at the overall safety workflow. As I had mentioned before, that we have kind of a three-stage process in which we have to do some analysis before, and then we perform an insertion of the safety mechanism based on the results of the analysis. And using those safe RTL, we perform a fault injection. And of course, the last process is how do we close that loop, that whatever fault injection that we have done is actually correct and the results meet our safety goal. So we will be talking about safety analysis, which is a process of finding or trying to create a plan to mitigate the faults ahead of safety verification, which is fault injection. And in this process, we will be learning the techniques on what we have done on this example IP that we have for the demo. and we will be progressing our flow towards the fault injection in the safety verification. And to close the loop, we will have the final FMEDA, which will be analysis to validation, full flow safety workflow. Okay, so before we move forward, I do want to talk about what is fit, or the basics of the fit computation. So fit is typically represented in terms of lambda, or also known as the failure in time. One fit is equals to one failure in 1 billion hours. So to achieve a safety target, the standard guides and gives us 4 ASIL levels, A being the lowest, B, C, D. D is being the highest ASIL target that needs to go for the most safety critical IP. For ASIL D, we are looking to achieve a fit of less than 10. For ASIL A and B, we are looking to achieve ASIL the fit for less than 100.
So Vedant, I have a question for you.
Sure.
Is fit calculated at the system level or the chip level?
Yeah, that's a great question. So fit is actually a vehicle level requirement. What it means is that we have to measure all the chips that have been made for a particular system. For example, if there are 100K cars made using the one design of a chip, they have to run at a minimum of 1 million hours altogether, to achieve a 1 million hour runtime of altogether, to see that one fit in 1 billion hours. So it's a vehicle level requirement as opposed to a chip level requirement.
Okay, thanks.
Yep. So how do we calculate the fit? So basically there are various standards available that you can use to calculate fit. The one we will be using for this experimentation is going to be the IEC 62380 equation. And as you can see, we have the lambdas associated to the technology that we are using. For analysis, we have the technology, mission, and package profile information. Once we have all that information, we should be able to receive a base failure rate of the system that we are trying to analyze.
So Vedant, I see that there's several profiles that seem to be inputs to this. Where does all that data come from?
Yeah, so most of the time, the standard guides us with some default values. For example, for the technology and mission profile, the standard will give us information based on the particular standard that we are using. In our case, we have a default values that are coming up and we are using, again, from the standard, but you can always use your fabrication or foundry data to override these default values and then calculate the overall base failure rate based on the custom profile settings that you have.
Oh, that's good to know. Okay.
Yeah, so let's understand another concept. Let's take an example of this very small circuit representation where I have two instances. So one of the things that is often talked about is each portion of the design or everything in the design contributing the same way towards the base failure rate. And usually that is a very vanilla information to use, that every portion of the design is contributing the same way, but that is not the real case. So the analysis technology and the algorithms that we use tells us that they analyze the design and they tells us which portion of the design is actually giving you higher fit rate. So we can give you, we have information available on which portion is giving you the highest contribution towards your fit.
So it looks like EP5 is the biggest contributor to fit. What do you actually do with that information?
Yeah, so Looking at this, as you can see, the highlighted portion, EP5 is the one which is getting contributed most with the other flops. EP is actually representation of a flop. So this report, this typical example report is simply saying that your EP5 is contributing the highest towards your base failure rate. And once you make a plan to protect EP5, you should be able to mitigate a majority portion of the faults in this setting.
Oh, okay, great.
So how do we perform exploration analysis? So we discussed about that we have to calculate the base failure rate. We have to do mitigation of faults. So how do we know ahead of time that which safety mechanism would be good or not? So the algorithm that we uses the cone of influence analysis between the start and checkpoints. So basically what it means is that we can trace the path between these generation and checkpoints and find the cone of influence and make a plan to mitigate those faults in this path. And when we are doing this, we also give you that what would be the safety mechanism if you were to do such protection.
So this looks like a really inventive method of getting diagnostic coverage for the design. Can you actually give more detail about this?
Yes, actually. So yeah, so this is one of our patented algorithms. What we actually do is we take the design into consideration and we define the generation points of your data and we define the checkpoints for your data. So just as I showed you before, so if input 1 and input 2 are your generation points, we will take these two as the generation points and you can define the checkpoint. So we will trace the path between these two inputs and this checkpoint. So anything which comes into this path will get tagged in the cone of influence, and anything else which is not in this path will be dropped from the analysis. So if you have very important data path layer or some data following, we can really follow the data from the beginning to the close. So it gives you a very quick information, and we can analyze the entire system altogether. Okay.
Okay, great. Yep.
Yep.
Thank you.
So we have talked about the fit. We have talked about how do we explore about safety mechanisms. How do we actually determine the safety mechanism? So the standard in chapter 5 guides us how do we find and determine the safety mechanism. So we have actually used the same algorithm to determine the safety mechanism approach. And if I want to show you, so we have actually mapped exactly the lambdas which are coming from the standard in our experiment. So we are able to map individual lambdas to the individual buckets, and that's how we are going to perform our FMEDA mapping. Okay, so to set and to perform this experimentation, this is the block diagram of our example IP that we have performed these experiments. It has various blocks. So it has a bigger contribution on the wishbone, which have SRAM. It has media interface, configuration register block, control unit, RX and TX block, and so what we tried to do is we tried to make an approach in which we were actually doing a combination of complex safety mechanism. So the complex safety mechanism is basically that we have a combination of hardware safety mechanism. On top of that, we also have some software safety mechanisms that we are trying to validate. So in this particular design, we did protect our design with both a hardware and software safety mechanism. So if you can see, the ledger tells us this pink color marking is for the hardware safety mechanisms. Flop parity, we have data path protections on RX and TX block, and ECC on SRAM. And then this orange color is the software safety mechanism, and we have some software safety mechanism protecting the SRAM, RX, and TX block. And as you can see, this is the safety mechanism list, that whether we have only hardware safety mechanism in case of configuration register, or both hardware and software safety mechanism in case of SRAM, RX, and TX block.
So we're at the analysis phase right now, and it looks like there's some safety mechanisms in here. So have we inserted the safety mechanisms during this step, or is this just an architectural suggestion for additional safety?
Yeah, so that's a very great question and contrast to point out. And actually, what we started our experiment is purely analysis, purely exploration, which is we can do this analysis and do this exploration exercise without actually modifying the RTL code. We can see what would be the effect of a safety mechanism on the entire system without even inserting the safety mechanism. So this portion that I'm showing, this is actually just the exploration side. We have not changed any RTL, existing RTL in this case. We are just seeing what would happen if we were to change the safety mechanism and add the safety mechanism in the design. But the second part, which is of course, like once you're satisfied with the result, we can always add the safety mechanism and redo the experiment to see whether we are still meeting the goal as we anticipated before or not. Again, both of these steps are before the fault injection, so you're saving a lot of time and energy in that process. So we are merging the analysis and exploration part right now.
So basically, this is exploration and what-if analysis to try to achieve that optimal safety level before you get to fault injection.
Correct.
Okay. Great.
So yeah, as you can see that once you do set those, we did set up that experiment and we prepared what type of safety mechanism were protecting those blocks. We were able to create an exploration FMEDA, the analysis side of it. Again, the pink is showing the software safety mechanism for a failure rate, and the orange is showing the hardware safety mechanism on a different failure rate. And we were able to see that what would be the effect of these hardware and software safety mechanism individually to these respective failure rates. And we are able to see some kind of diagnostic coverage around that. So as you can see, just adding the flop parity on the configuration register block for hardware faults, we are able to see around 60% coverage. But when we do add end-to-end protection on a data path, we see around 85% coverage, and software safety mechanism gives us around 95% coverage. So this becomes our the initial analysis document, which serves as one of the key pieces that we are trying to validate in this flow.
So the DC exploration numbers, right? Those are the ones that those metrics are the ones that you're going to validate. Is that correct?
Correct. The DC numbers is the one which we are going to validate. And in conjunction to just validating these numbers and preparing that for that experiment, we also were able to generate a targeted optimized fault list for individual failure modes. So for hardware safety mechanism, we have a fault list. For a software safety mechanism, we have a different fault list. So we were able to generate a fault list for all of these blocks respective to their failure modes. And these both becomes key essential pieces for our next phase of activity. Now let's hear from Samson. on what he has done for the safety analysis side of his on one of the production design that they have been working on. They have used the same techniques that we are talking about. So over to you, Samson. Thanks.
Hello, everyone. Welcome. My name is Samson Wong. I'm a staff design engineer at ARM in Austin with the Central Engineering Division with the Systems Group. I've been with ARM for 4 years and working on functional safety. Today, we are going to talk about the functional safety explorations using Citivscope at ARM. So below is the agenda. We're going to talk about the overall flow of exploration and the following steps, like a baseline RTL netlist. Basically run the exploration based on the unsafe IP and then do the what-if analysis of deploying different safety mechanisms, compare the metrics from these different explorations, and implement the one that meets our safety goal or ACL target, and then finally rerun Citivscope to validate the safety metric and compare that against the original unsafe IP prediction. So here's animation on the overall flow. We start with an unsafe design, RTL on that list, and run Citivscope to do the exploration and generate some report. And this can be an iterative process. If the exploration meets our ACL target or safety goal, then we would move forward. Otherwise, we will refine and try different safety mechanisms. And this process will continue until we decide on the safety mechanism we want to implement and try that design, and then generate a safe design, could be RTL on that list. And then we rerun Citivscope again to check our metric and compare with the previous prediction in the other orange box.
So you have this orange ledger on the top. I assume that everything in this flow, which is orange color, has to do with a Citivscope run?
That's correct.
Okay, so you do the Citivscope run on the and you do the analysis report, exploration, choose the safety mechanism, and then compare it. Okay, that's good.
Okay. Unsafe IP, the Citivscope gives us a series of reports. Specifically, we are interested in the things like base failure rate and the lambda permanent, lambda transient, and it has also give us the PPA, power, performance, area impact, the number of registers, latches, internal nodes, and so on, and give us a very meaningful report at the module, instance, and register levels.
Okay, great. So these module, instance, and register report, they're like with respect to the fit or the base failure rate contributions?
Yes.
I see.
Okay, so we apply the same methodology on different safety mechanisms to compare their metric to see what is the, for example, SPFM, the single point fault metric, permanent and transient. How does each of these different safety mechanisms that we explored would provide us, basically we line that up against our safety goal and also compare of their costs, like the number of latches involved, registers and flops and gates and so on. So basically we have a result together with a cost kind of metric. So we do this on many different IPs the customers want. So we can see for which kind of design we can use what kind of safety mechanism and what is the associated cost.
So you mentioned that you're doing this analysis at safety mechanism. Was it is it hard to set up the safety mechanism information with the tool when you have to use it?
It's quite straightforward because the RTL analysis is not changed. This is a hypothetical situation. The tool can do the analysis based on the safety mechanism you specified and provides the result in the report.
I see.
We now have a decision metric. So for different configurations of the IP and then against different safety mechanisms, what is the result? For example, in terms of SPFM permanent and SPFM transient. So you do the decision metric, basically a matrix, then you pick the one that meets your criteria and use that to go for implementation.
I see. So in this one, you're using one or more than one safety mechanism at the same time and comparing the results of each exploration with each other?
Could be single safety mechanism or multiple safety mechanisms. Yeah, so can be single or a combination. Yeah, you can do different things to try them.
And you played with so many safety mechanisms. Is there like a good safety mechanism or a good process that yielded out of this experiment?
I think the one thing that we like a lot is the river flow mode or the end-to-end safety mechanisms. I think that is very powerful. So we like that a lot.
Okay.
So once we give the development team the safety mechanism for them to implement, we then have a design that actually contains the specified safety mechanism. It could be in the form of RTL on the list. So again, we take that now safe design, we rerun safety mechanism and rerun safety scope to check how does the actual functional safety metric, for example, SPFM permanent or SPFM transient, compare with the earlier prediction from the what-if analysis. So then we have the before and after comparison.
Okay. And because you did before insertion of safety mechanism and after insertion of safety mechanism, were these results close enough? Like, what was your what is your findings around that?
From the experiments that we have run so far, we find that to be quite accurate. Yeah.
Okay.
So finally, as a conclusion, we find the tool safety scope to be very user-friendly. It's quite simple to set up, and the runtime is quite reasonable. And also, we are getting wonderful technical support from Iran. And the tool is very flexible. So depending on the design phase you're in, the tool can allow you very early safety exploration. For example, using RTL before netlist become available, and then do that again later when netlist is available. So you have this on the same phase of design, do the RTL-based analysis against the netlist-based analysis. And then do the same thing at different phase of your design flow. And the tool is very powerful. It supports both endpoint and cone of inference based safety mechanisms. Basically, the endpoint is the basic one, where you for example, for parity. That's the point where you want to check the parity, or you can do like end-to-end safety mechanisms, specify a generator on one end and a checker on a different end. So we find that to be a very powerful to be able to support both of these flows. And also the tool generates a report that's quite informative. give you very detailed permanent and transient fault coverage reports for the nodes that are covered and not covered. And finally, we give a sample command flow, command line for running safety scope in our environment for a hypothetical safety mechanism, DCLS, or dual core lockstep for a hypothetical configuration of the IP called config1. And those are the switches we need to supply to do a DCLS exploration on config1 and generate a report and log files. And that's all I have.
Okay, so as my final question, I'm simply going to ask, like, in all of your experiments, did you find that you were able to save a lot of time and effort using this experimentations with safety scope in overall flow?
Yes, I found that improve our productivity a lot, and it enable us, as I said, doing exploration early on before the design is finalized, and provide us a overall view, give us a better feeling or a better data point of how different safety mechanisms compare against each other and at what cost. So we find that to be very useful and very for our helped us a lot in terms of improving productivity of the design team.
Okay, great. That is very good to hear. Thank you, Samson, for spending the time and taking the effort to tell us more about your experiments with Safety Scope.
Thank you, Vedant.
Hello and welcome back. Yes, so in this section, we're going to be talking about fault campaign, or commonly known as fault simulation. Yeah, so what we have done to progress our experiment is we have taken the analysis input from safety analysis portion. We now have the fault list available. We now have the exploration FMED available. And we have also went ahead and inserted those safety mechanisms that we chose in our analysis step. We have also gathered the regression or the stimulus data. Now we will be performing fault injection on individual failure modes to individual portion of that design. So what our expectation is that once we perform all this fault injection on various portion of the design, we want a classified fault list out of this experiment that can be used in our audits or in our any traceback documents that we can use, that these many faults were detected and what was the classification of that fault.
So Vedant, running a fault campaign on every failure mode seems like it could take a really long time, especially on these large, complex designs. How do you optimize this process?
Yeah, that's the crux of the entire safety workflow. And I think it is a two-part answer. The first part is really focused on how do we make sure that we are reducing the number of iterations. And I think that process comes from doing the analysis correctly. And what we have done is, before we went to fault injection, we performed the safety analysis and we chose a safety mechanism. Once we were happy with those safety mechanism, at that very point, we generated the fault list. The second portion of this is if your fault injection is really done at the optimal level. For example, whether you're able to do concurrency, multi-threading, and all sorts of things. And of course, you can do it with any kind of serial fault simulator, but having all these performance improvements really help to perform an quick or single iteration or less iteration fault injection and fault detection.
Okay, thanks.
Yeah, so on the fault classification, We are looking for information in 4 quadrants. The standard tells us these 4 categories. And basically, if we are able to categorize all the faults that we have in fault list in these 4 categories, we should be able to validate our claim that whatever we said in the analysis is true after doing the fault injection. So the first category is detected, not observed. It means that whatever alarm we had, whether it's hardware or software, did detect the fault injection, but the output did not change. The second category is detected observed. In this one, alarm and the output both detected the fault. Both of these categories are somewhat good for our system because we have detected the fault. One is completely safe, one is in danger but can recover. This blue quadrant is basically undetected, unobserved. So nor the alarm fired or the output changed. So it's a potential fault. The problem may occur with different faults or different input, but it's a potential fault at the moment. And the final category, which is the red flag with the color, is the unrecoverable failure, in which the alarm or the safety mechanism was not able to catch the fault and output is changed. So these are one of the dangerous categories of fault that we really need to pay attention to. Okay, so how did we do our experiment and how did we perform fault injection? So again, our safety mechanisms were 2 parts. The pink one were the hardware safety mechanism, which was the hardware fault simulation, and the orange one were your software or known answer test. So what we did is we targeted these blocks and we performed fault injection using the optimized fault list in these blocks. And what we were able to generalize in terms of detection report is we were able to see which fault node was detected for what kind of fault. And we were also able to see which was the alarm, whether it was a hardware alarm or a software alarm, which did catch it.
So on the last slide, you showed those 4 quadrants with all the classifications, but in this table, you're only showing detected. So are the other classifications important, and why aren't they here if they are?
Yes, so detected is a superset of the detected observed and detected unobserved. In this case, I am simply categorizing all the faults which were caught by my alarms. The other portion, which is the dangerous fault, in which alarm did not catch it. In this particular experiment, I did not have those faults, any dangerous faults, so I'm not showing them. And there are some potential faults which I'm not showing here because there were very few, as opposed to thousands and thousands, and there were very few. So I think yeah, this detected portion is a superset of both detected observed and detected unobserved.
Okay, I see.
Okay, the final section is basically the closed loop. Yeah, so in the closed loop, what we are trying to do is we are trying to take the analysis portion, which was our estimated FMEDA, and we were also able to generate like an optimized fault list. And then progress that analysis side of the results to the fault campaign. Using the fault campaign, we were able to classify the fault classification report. And now we are trying to use this fault classification report of individual nodes and with respect to their fault detections into the final validation, which should give us the final FMEDA. So this should conclude our flow of analysis to validation of our complex safety mechanism. Okay, so we we already had prepared our exploration FMEDA. This now also shows us the metrics with respect to our validated FMEDA. As you can see, I still have those hardware and software safety mechanism with respect to those failure modes. And you can see that individual failure mode and safety mechanisms were giving us some kind of estimation. And now we can see the actual estimated metrics with respect to the fault injection. So this gives us the full validated FMEDA that can be used in the audits.
So, Vedant, I see a minor delta between exploration DC and validated DC. Is that expected?
Yes. So, and actually, that's a very good point. So, what happens is that the final validated DC is really dependent on so many factors. One of the factors is whether we were able to inject and perform the fault injection for both flavors of the fault, stuck at 1, stuck at 0. And if our input is not sufficient, we are only able to perform fault injection on 1, then we have some gap in between in the fault injection uh, with respect to the fault stimulus. So this could be one of those things. The other thing is now we really have taken the RTL and modified and added new safety mechanisms. So there is a minor delta between the two which can be expected with respect to that. But as you can see in several other instances, for example, in terms of SRAM, where we were able to do 100% of the fault injection, we do match the estimated metrics perfectly.
Oh, that makes total sense. Thank you.
Yeah.
That's very good information.
Thanks. So yeah, so just on the recap side, so we started our experiment on total unsafe design with just performing the analysis, and now we have the final validated metrics after performing the fault injection. And this concludes our analysis to validation and validation of complex safety architectures flow. Thank you. Back to you, Anne. Hello everyone, welcome to the tutorial demonstration. I will be walking you through the example IP that we have selected for this demonstration. We will be starting our exercise by doing safety analysis and then progressing into fault simulation, and then finally showing you how we close the loop by using the classified fault list from our simulation results. So really on the safety analysis side, the first thing that we talked about was the fit contribution reports and the base failure rate. So I have set it up my example IP using safety scope, and I'm using the analysis mode to it. What really am I doing here is I'm providing all my RTL file using this configuration files, FUSA INI, and I'm using the safety scope in the analysis mode. If I run this particular step, what you will see is I will be able to see the associated technology type. So I have some standard cell in the design. So I'll be able to see the lambda numbers with standard cell. And I also have some SRAM in the design. So I'll be able to see the lambda numbers for SRAM. And then towards the end of this report, I see the overall lambda and overall lambda transient for this particular IP. Since this is a base failure rate, we have no safety mechanisms in this. Our DC numbers will be 0. So as an output of this run, the base failure rate, we are now able to see the fit contribution report with respect to each instances. We can have more finer details, meaning we can see the fit contribution at the very least the leaf level, but let's keep it at the instance level. So if I sort this report out to the highest contributor instances, I'll be able to see that the Ethernet Reg 1, which is the configuration register block, is giving around 3.3% contribution towards my failure rate. Then I have some MAC control blocks. I have the media interface, the RX ETMAC, the TX ETMAC, and the Wishbone is the highest contributor with 73%. And inside the Wishbone, I have two blocks, RX and TX50, which are contributing the highest. So in my next experiment, in the next step of this experiment, I will be utilizing these blogs, the information that I've received from Safety Scope, on selecting the safety mechanisms and seeing the effect of that safety mechanism towards my overall diagnostic coverages. And if I'm happy with those diagnostic coverages, I will move forward and really insert them. So to set up the exploration, I've utilized the information from this fit contribution report, and I've tried to set up experiment that what will happen if these safety mechanisms were to use that I'm experimenting with. So in my first exploration run, I'm using this configuration register block, and I'm trying to protect this with the flop parity. And the way I do that is I define the safety mechanism file. So if you see that my setup is exactly same as before, except this safety mechanism file that I've defined. So in this one, I'm using the Ethereg1 block, and I'm trying to protect with the flop parity. So if I do that, and if I run this particular step, you'll be able to see that by doing this, I am now able to see some diagnostic coverage. So right now my diagnostic coverage is around 7.3%. So these are whole numbers, not the percentages. So the percentage is a factor multiplied by 100. So 7.3% for permanent and 10% for transient. And similarly, if I want to explore with other blocks which were heavy contributor, here I can set up all those experiments at the same time. So in my next run, you can see that I have set it up on the Wishbone FIFOs. I have protected both TX FIFO and RX FIFO with duplication, and I've also added some protection to the SRAM module, the BDRAM module, by some memory ECC. So providing all this setup all together with the tool, if I run this step, you'll be able to see that now my diagnostic coverage has jumped to, for the permanent, it has jumped to 43%, and for the transient, it has jumped to 54%. And what's interesting is that I provided the memory CC protection to my SRAM, BRAM module. And as you can see, like for just the SRAM module, I have full 99% protection for both permanent and transient. The good thing about this is that I can see what is the effect of a safety mechanism on individual technologies. So for standard cell, I can see it's 43.1%. For SRAM, I can see it's 99%. And this number that I get here is the overall diagnostic coverage for the entire IP in under analysis. So we can use these tools in two ways. If you are concerned about only running a fault simulation and optimizing your fault simulation exercise, and choosing your safety mechanisms correctly, inserting them, and then running the fault simulation exercise, you can use these tools in the batch mode, and it does a pretty good job in telling the information by these text reports and log files and whatnot. The other experiment, the other portion of this is if you want to create a full-fledged FMEDA, we can also use the FMEDA extension to these FUSA tools, and we can create the entire FMEDA using the GUI experience. So I will also be demonstrating how I create the FMEDA. Will not go into too much of detail, but I will show you how we created the FMEDA for this experiment. So if I open up this GUI extension, which is for all these FUSA tools, I can create a new project and I can say DVCon India, and I can hit run, create. What it does is it loads some of the default values. It has loaded some of the default failure modes here. It has also loaded some of the default safety mechanism library for me. If I go in the safety setup, it is asking me to create a new session, so I can name my session as exploration, because we'll be doing some exploration. I hit OK. It loads all the default files into it. These are the same defaults which Safety Scope was using to calculate the base failure rate and when we were doing the exploration. So if I click on this FMEDA tab, it is asking me to build the instance list, and I can provide the RTL design here. Once you provide your RTL file list, I can set up which I can build this instance list, and I can see the entire hierarchy in this table. So now the next thing is to actually create the FMEDA. So I can create multiple parts of it. For this experiment, I'm creating only one part. I'm gonna call it Ethernet MAC at the top level, and then I can add, let's say, 4 subparts to it. So for this experiment, we are manually assigning different instances to these subparts. So the first one is I'm assigning the configuration block. The second one is this TX50. The third one is this RX50. And finally, I'm going to associate this SRAM module in my fourth instance. So as you can see, this FMEDA is starting to shape up. Now I have the subpart information. I also have the instance mapping done. The good thing is I can really name these subparts. So the first one is the configuration register block. The second one is the TX50 RX50. Last one is the SRAM. So I can name my subparts accordingly, and I can see the mapping done. So once this portion is done, I can just hit this run button on the top. And what it will do is it will create the safety scope runs in the background. And once that is finished, I will be able to see the associated FMEDA lambda numbers and some metrics around it on this sheet. So the really good thing is that the tool does this in the background, and I'm able to get all these information filled up in this FMEDA sheet automatically. And then I can go and set up more runs and more experiments out of it. Okay, so once I have the base numbers, the next thing to do is to explore with safety mechanisms. I'm not going to go into too much detail. Let's set up a safety mechanism on one block. So for this, let's choose a failure mode here. And I can just do that by click of a button. So once I add a failure mode on my configuration block, I can choose a safety mechanism. So if I create the file new, I can say reg sm, and it will open up the hierarchy that safety mechanism is going to be explored at. So now I can see what are the safety mechanism that I have in my choice. So for this experiment, I'm gonna say explore with the endpoint parity. and I can say save, go back to my FMEDA. And since I've only changed and added a safety mechanism to this one instance, I can just select this one and I can say run. And what it will do is it will kick off a safety scope session in the background. And now you can see that I have the safety mechanism added to that block. So this 37% is really the safety mechanism information, the effectiveness of that safety mechanism on this block. Now, I could have done the same thing using the batch mode. So if you look at this top right corner here again, so what I've done is for this experiment, I have pre-explored with some of the safety mechanism, and I went ahead and I actually inserted those safety mechanism in my RTL. So in my next step, I will be progressing this tutorial to creating of the fault list. So fault list I have done at the configuration block level, which we explored with flop parity, the TX50 and RX50. So if I were to use the same same batch mode setting, same settings in the batch mode, I can simply add the safety mechanism information here using this switch. This is the same file with flop parity on the Ethernet register block, and I can say 1.1, and you will be able to see I have the same diagnostic coverage which we got when we set up the FMEDA in the GUI. So similarly, I have run these steps for TX50 and RX50, and if you see in the RX50, I've gotten around 47%, and similarly on the TX50. What we have really done is we have created the fault list. So for configuration register block, I have around 699 nodes which are ready for fault injection. For TX50 block, I have around 5,342 nodes which we will be performing fault injection on. And similarly on the RX50 block, I have around 727 nodes available for fault injection. Yeah. So yeah, once we have created the fault list, we already have the safe RTL, and I've pre-run some of the test stimulus for this tutorial. So the next step in our tutorial is really running the fault simulation. So for our fault simulation, I will be using the tool called Kaleidoscope. I'll not go into too much detail, but Kaleidoscope is the fault simulator, and we will be using the concurrent fault simulation with the help of running some parallel fault injections using multiple cores and multi-threading. So I have in my test stimulus list, I have around 5 FSDVs that I will be using for as test stimulus. Now these test stimulus were creating using UVM test bench random method, and we will find out if our safety mechanism that we have really inserted in this RTL are really doing a good job and effective to catch all these faults. So the first fault simulation, I'm dividing it into the same level of blocks. I'm performing it at the configuration level, and I'm using the same fault list which was created in that fault list database. So as you can see, I'm using the use of database which was created. Now this is the same database which will be created using the GUI or the batch mode. So I'm tagging the same fault list database here, and if I perform the fault run, as you can see, it is taking the entire 699 fault nodes, and it is going to run for both stuck at 0 and stuck at 1 flavor. So while this is processing, I have also run the other two blocks in parallel so that we have some results of fault simulation. Um, so I was able to finish the fault simulation for all the three blocks. So let's look at the reports of individual block. So let me open up for the block one. Um, as you can see towards the end of it, the tool will give out a nice summary report of how many total faults were there, which were analyzed and injected, and what was the portion of them which were detected and which were not detected. So we can quickly see that there were 1,398 faults total, and out of that 1,330 were detected, 68 were not detected, and the finer details are that 60 were not even injected, and 8 of them were reported as no deviation from the output. So when we will be utilizing these reports for our validation, these numbers definitely do come into picture because it will not be giving us the exact amount of coverage, as we have some fault nodes which are not injected. And of course, we can come back and rerun this fault campaign um, for just these 60 faults with a different stimulus. Similarly, for block number 2, we had around 10,000 faults altogether. We are able to detect 10,428 faults. And similarly, for block number 3, uh, we had around 5,454, 2727 for both stuck at 1, stuck at 0. And we are able to detect around 5,298 faults. So for final metrics, we will be using the classified fault report, which comes out of our safety verification of the fault simulation tool. So this is an example of a classified fault node report. These are the actual nodes which have been detected for both stuck at 0 and stuck at 1. So we utilize this information with our tool, Safety Scope, the analysis tool, and will give you a final qualitative metric on the effectiveness of your safety mechanism. So let's go back to our GUI where we were building the FMEDA. To finish off this experiment, we will do a comparison between the metrics of fault campaign between these blocks. So I have a second session, which is the FMEDA for validation. And if I go here, I can copy the same settings to this session from the exploration design. And if I go back to this FMEDA, I can build off the same instance list. Similarly, I can put together the same FMEDA that I had before. And if I want to see the metrics for the configuration block, all I need to do is I need to provide the same classified fault list, which we generated using the fault simulation of that block. So if I go here, and instead of providing the safety mechanism, I can import from the metric report. So these are the metric report for the EtherEdge block, and they have the same ATD KS tag. And I go back to my FMEDA of this one, and I can say save and run. What it will do is it will process the validated metrics for the configuration block, but since I have not provided the information for the other blocks, it will not give me the metrics in terms of DC for those. So now you can see that I have around, so let me undock this window so that we can see the metrics side by side. As you can see now, I have, for the configuration block that I was making right here, I have a slight delta in DC, and that is because I had some of the faults which were not even injected due to not enough stimulus. So that explains that why my estimated number is not reaching the validated number. So if I run this block with more stimulus to accommodate those 10 or 15 faults which were remaining, you will see that this number is going to be in line with my estimated metrics. And that is how we close the loop from starting from analysis to validation. Um, I'll summarize our experimentation today, the tutorial that we have shown. So we really started off our tutorial with an unsafe RTL, where we used a tool called Safety Scope to explore what type of safety mechanisms will be absolutely good for us. And we explored with a few safety mechanisms. Once we were happy from those safety mechanisms and the metrics that we got out of Safety Scope, we went ahead and actually inserted those safety mechanism in the RTL, as in any safety team would do. After inserting the RTL, we created the optimized fault list to prepare ourselves for fault injection. And after we had the fault list, the safe RTL, and the test stimulus ready, we performed the concurrent fault simulation using Kaleidoscope. Um, After Kaleidoscope finished the fault simulation, we really got an output called a classified fault list, which had information about which fault node was detected for which particular fault. We used that classified fault list back with Safety Scope to give you a qualitative FMEDA metric. This is different from the quantitative metric, as in we actually look for each and every node and we calculate the DC coverage on the basis of how much contribution that particular node which has been detected is providing to your IP. So with that, this concludes our full analysis to validation flow. I hope that this tutorial was helpful to you. And if you guys have any questions, please let me know. Thank you.
Great. Thanks, Vedant. That was great. Okay, and the final slide in summary. As you can see, validation of complex safety architectures is challenging for a lot of reasons, and achieving accurate metrics and your optimal safety architecture early in the safety workflow before running your fault campaign can save months of time, as we've shown here, and accelerate your time to certification so that you can actually get your product to your customers on time. So hopefully you enjoyed this webinar and learned some things from it. And thank you very much for joining us today.
Thank you.
Hey, thanks a lot, Vedant and Anne. It was a very detailed and elaborative tutorial on the complex safety mechanism architecture. I like the flow which you guys have created over here. It is very valuable for a lot of people who are new to the this domain, as well as those who are already involved in this domain. I'm sure even novice people would be definitely gaining a lot of insight into the safety mechanism from your tutorial. We have a few questions. I will be going over those questions over here. The first question is, do you consider the area, total gates of the design, that the part or subpart as represented in FMEDA to calculate the fit for the each part and subpart?
Yes, I can take that. And so yes, we do calculate and we do analyze each and every cell. What we do is our analysis engine do a pseudo synthesis under the hood, and we calculate the number of transistors for each cell. And based on those transistors, we calculate the overall fit metric for each subparts and rolling up all the way to the top at the part level.
Thanks, Vedant. The next question which is asked is, could you please explain how software fault list is different from hardware one? Isn't the fault list common for a particular FM based on the area of design it corresponds to?
Yeah, so that is a good question. So actually, our algorithm is very unique and very innovative in trying to save you as much as possible in terms of optimizations. So when we talk about fault list, one of the key concepts is we should be looking at the safety aware and safety critical nodes. So the software safety mechanism, we calculate each and every node which is getting protected with that particular safety mechanism. Similarly, in the hardware safety mechanism, we calculate whether it is protecting individual flop or individual gate or both. And we look at these combinations of whether the software safety mechanism is providing to one portion, the hardware is providing to the other portion. And that's why these two can be different depending upon the safety mechanism coverage that they are assigning in overall design.
Thanks, Vedant. The next one I have is, do you see a large set of UUs in the first iteration on campaigns? If yes, how did you overcome this challenge?
Yes, so I think this is one of the questions that Anne asked me during the tutorial, that how do we optimize the iterations and fault campaign this because this is a very long process. So the overall flow talks about the analysis. So it's a two-part answer. The first portion is that we really need to optimize the analysis portion. And analysis portion comes from that, are we using the right safety mechanism to protect the design? Are we creating the optimized fault list? Are we going with the maximum possible optimization in terms of test stimulus? And the second portion comes in the actual fault simulator, where you need to have the concurrency, the multi-threading, and all those parallelism involved to reduce the overall runtime effort of the fault simulation itself. So together with the optimized analysis and the optimized simulation, we create this flow, and we were able to save a lot of iterations.
Yeah, thanks. The next question from the participant is, what is the criteria for deciding the blocks for the fault injection campaign? Do you pick all the blocks or only some of the blocks? If yes, what is the criteria?
Yeah, so we will be looking at the blocks which definitely are protected. So our analysis tool will be able to give us the actual node list which have some protection. So those blocks, those nodes become absolutely necessary to be part of fault injection, and we automatically optimize and give you that information. So that is the first pass. The second pass is it also depends on your safety goal. If a block is in your path of your safety goal of safety critical path, then again we will choose that block as well.
Okay. Thanks, Vedant. I have one more question to go. Can you elaborate more on the fault list generation? Is the list generation based on the analysis from previous step? How do we generate such a list from netlist?
Yes, so our both methodologies, only the analysis portion and the fault injection portion, both can take the RTL and netlist also. They will be both processed in the same way, and we will be able to generate the fault list on the basis of the definition of safety mechanism. So I'll give a very quick example. If a safety mechanism is like a hardware safety mechanism, which is going to protect all the flops in your design with some sort of parity, then we will look and analyze the entire design, and we will create an optimized list of all the flops which have been protected with this parity. Anything combinational logic or anything which is not covered by this parity will be dropped automatically. So this is where our optimized algorithms comes into picture of generation of fault list.
Thanks, Vedant. There's one question from my side, from my education. You're talking about fault campaign, and you're talking about the injection and classification. So there you use a term called a software no answer test. May I know a little more about that?
Sure. So a software known answer test is very similar to a software test library. A known answer test, the name comes from because we have done a golden simulation and we know what are the initial vectors and what are the known state of those initial vectors. So whenever we do a fault campaign on this software-based known answer test, we will always be comparing to this known state or a known answer test that we have already performed with respect to the new fault injection that we have just started. So if there is a deviation, then we know that there was a deviation between a known answer test and the new fault simulation that we did, and it will write into your actual register in the hardware. If both states are same, then we pass.
Okay, thank you. Thank you very much. I like this particular session too much. I'm sure many participants would have also liked. And with this, I can conclude this particular tutorial. Thank you, Vedant. Thank you, Ayan. Thank you very much.
Thank you.
Thank you very much.